Today's topic is third law of thermodynamics. First law of thermodynamics was that energy is conserved. Second law of thermodynamics, that is for any spontaneous process entropy always increases. Okay, third law of thermodynamics. So according to third law, the entropy of an ideal or perfectly crystalline solid may be taken as 0 at absolute 0. This is the third law of thermodynamics. What is that? The entropy of an ideal or perfect crystalline solid. That is may be taken as 0 कब? At absolute 0. Okay. So this is the third statement of third law of thermodynamics. We can take it as limit t tend to 0 s t that is equal to 0. This is called third law of thermodynamics. Say limit t tend to 0, okay, st, that means entropy at absolute 0 kiski? Of a perfectly crystalline solid, that is 0. This is called third law of thermodynamics, because you know ki absolute 0 temperature, that temperature is so low that constituents in a crystalline solid are not expected to have any movement. You know, when temperature decreases, kinetic energy decreases. So when temperature is almost 0, in mathematically kinetic energy is equal to translational kinetic energy 3 by 2 RT. R is gas constant, T is temperature in perfect crystalline solid means when particles are arranged in a means ideal, this is an ideal arrangement we can say. Okay, means if particle is in an ordered manner, perfectly ordered manner. Okay, so when they are perfectly ordered manner, first of all, crystalline means when there is a uniform arrangement. Okay, perfect means there is no chance of any deviation of that arrangement. Okay, that is called perfect crystalline solid. Okay, Ralam, got it? Crystalline, it means uniform arrangement, okay, regular arrangement of constituent particles, and perfect means there is no chance of deviation from that arrangement, that is called perfect crystalline solid, and its entropy is taken as 0, because kab at absolute 0, because when temperature tends to 0, that is temperature is so low that there is no movement of constituent particles. Okay, and their energy is expected to be 0, because if T is 0, kinetic energy is 0. Okay, so this is true only for ideal crystals, because you know whenever we are arranging something, okay, very slowly, even then there is some flaw. Okay, so ideal word is used means there is no chance of deviation from that arrangement. Okay, so that's why we call it as ideal crystal. Okay, means that crystal which is free from any defect, there is no imperfection. Okay, because any deviation from ideal arrangement is called defects or imperfection, called imperfections or defects. So ideal crystal is free from all types of defects. Okay, that's why we call it as, this law is applicable only to the ideal or perfect crystals, which is free from all types of defects. There is no defect at all. Done. Now application of third law of thermodynamics. So its most important application is, it helps to calculate the absolute entropy of any substance at room temperature. Okay, you know delta S. What is delta S? That is entropy at one state minus entropy at another state, because entropy is a state function. Entropy is a state function. So at temperature T, let us take its entropy as St, and at temperature T equal to 0 Kelvin, its entropy is equal to S naught. Okay, means St is entropy at temperature T and S naught is entropy at 0 Kelvin, means at absolute 0. So what is change in entropy then? It is entropy at temperature T Kelvin minus entropy at temperature 0 Kelvin, right? And according to third law of thermodynamics, yes, according to third law of thermodynamics, S naught is equal to 0, that we have done. S naught is equal to 0. Okay, so that implies delta S is equal to St. Delta S is equal to St. So in case of solids, St equal to delta S, and that is equal to, temperature varies from 0 to T. So it is Cp dt. How this Cp dt comes? You know delta S is equal to delta H over T. We have done it. Yes, beta, final minus initial. Finally temperature is T Kelvin and initially temperature is 0 Kelvin. Okay. So when temperature changes, entropy changes. Okay, because it is a state function. And what is state function? Which depends on state. So at state 1 temperature is 0 Kelvin and at state 2 temperature is T Kelvin. Means S2 is St and S1 is S naught. This is initial state and this is final state. Okay, initially temperature is 0 Kelvin and in the final state temperature is T Kelvin. Okay, that's why S naught is not final, S naught is initial and St is final. Okay. Okay. So now you know that Cp is equal to delta H over T or delta T and delta T, but difference is T minus 0. So it is T only. Okay. That's why delta H is equal to Cp delta T or dH, small change is Cp dt. That's why we write it as Cp dt integration, because temperature varies from 0 to T. That's why we write it like this. And the value of this integral can be obtained if you plot the graph of Cp by T versus T. If we plot the graph, this T is in Kelvin, okay. So, if we plot a graph, the graph comes out to be like this, 0 something temperature, higher temperatures, okay. So, value of integral we can obtain by plotting graph between Cp by dt, Cp by T versus T. और this is area under the curve between 0 to T. Let us take this is T. So, this area under the curve is equal to this integral. And what is Cp? It is heat capacity of the substance at constant at constant pressure, okay. Cp, okay. And this Cp, because there is Cp value, that means this value is constant within that range 0 to T Kelvin. Okay, in this range its value is constant. We suppose it to be constant. So, now as you know, St is equal to 0 to T Cp dt by T. So, it is equal to Cp, and what is integration of 1 by T? Cp is constant. So, integration is 1 by T dt. So, what is integration of 1 by T? We have done that part. What is the integration of 1 by T? Integration of 1 by T. Anybody? Integration of 1 upon x is natural log of x. So, integration of 1 by T, that is equal to natural log of T. So, Cp natural log of T and natural log of 0, okay. So, simply it is natural log of T. So, it comes out to be 2.303 Cp and log of T. Okay. St is 2.303 Cp log of T. Okay. Now, what about liquids and gaseous? So, for liquids and gases, total absolute entropy at a given temperature will be sum of the entropy changes which the substance has to undergo, okay. See, I have drawn that picture before. See, if we plot the graph of entropy versus temperature, then initially it increases for a solid, then it is like this, then again say this is at melting point, or we can say freezing point, this is at a boiling point. Okay. So, del entropy change in this case is equal to, yes, anybody, can you tell me? See, first is 2, okay, better to write like this, 0 to T Cp of solid, 0 to freezing point, okay, dt by T, right. This is from this part 0 to Tf. Now, what about this? Yes, area under the curve, but value we can obtain like this. Now, plus this is the area under this curve. Now, what about this? This value is actually entropy of, yes, entropy of phase transformation, entropy of fusion from solid to liquid, solid to liquid. So, it is plus delta H fusion divided by freezing point. So, now we reach here. This is first part, this is second part. Now, third part, liquid. This is liquid only. What is the liquid range? From liquid freezing point to boiling point. From freezing point to boiling point. Now, it is Cp of liquid dt by T plus, yes, now we reached here. This is third part. Now, liquid to gas at boiling point. So, it is enthalpy of vaporization over boiling point. Okay. Then, now it is gas only from Tb to any temperature T. So, it is Tb to any temperature T, that is Cp of gas dt by T. This part is not in the syllabus. I have just shown it because this is very easy concept. You can apply anywhere. Okay. Good. So, this is total entropy change from solid to gas, from 0 to any temperature T. Done. Now, standard entropy change. Standard entropy change, that is delta S naught. So, standard entropy change, this delta S naught is equal to, sum of the entropy change or sum of the standard entropies of products minus sum of the standard entropies of reactants. Okay. Delta S naught is sum of the standard entropies of the reactants minus sum of the standard entropies of the reactant. Means standard entropy change is sum of the entropies of the products minus sum of the entropies of the reactants, because in a chemical reaction reactants are converted into products. So, final is product and initial is reactant, right? Have you done all those questions? So, if we talk about free energy of formation, standard free energy of formation. So, standard free energy of formation equal to standard enthalpy of formation minus T minus T delta S naught. Okay, and standard is at 298 Kelvin temperature and 1 atmosphere pressure. Okay, these are called standard states in thermodynamics. I think we have covered all the topics. So, standard free energy change is related to equilibrium constant. This topic we will cover in our next chapter, that is chapter is equilibrium constant, but there is one question, 20th number question, that has this formula we have to apply. K is equilibrium constant, okay. R is gas constant, T is temperature, and natural log to convert into common log we have to multiply by 2.303.